Welcome to another tutorial. In this tutorial I will show you how I made a remote control tank. I have used the drive mechanism from an old big track. I decided to use an infrared remote control in order to move it around. In this tutorial I will be discussing pulse width modulation and various H-bridge configurations in order to control the motors, but first of all let's have a look at the finished project.
By controlling both motors at once, we can have forwards and backwards motion. By making the motors move in opposition, we can have rotation. Unfortunately, this particular drive mechanism does not move in this matter reliably, but others should.
As you can see, this is a temporary construction made in order to demonstrate certain key principles. I have kept the components on project boards in order to easily dismantle them when I have finished. I have decided to use two separate power supplies. The motors are powered separately from a 3-volt battery pack. The 9-volt battery controls the relays and the Arduino board. I am using a 5-volt regulator from the 9-volt battery as the relays operate at 4.5 volts. I am not using the Arduino Uno to power these relays directly, as they may take too much power than the board can supply. I have used various capacitors in order to reduce the interference produced from the motors. Diodes are placed across the inductor of the relays in order to suppress the back EMF when they are switched off. This is the remote control that I am using. I have assigned forwards and backwards motion to these buttons. Clockwise and anti-clockwise motion are assigned to these. This button will stop all motors running. I use these buttons to operate only one motor, although this particular drive mechanism is not particularly conducive to such movements. I have placed certain motor test buttons to the number so that I can check my wiring to the motors. It will run a particular motor in a direction for 1 second and then stop. I'm going to show you now various H-bridge configurations with which I have experimented.
This is my first motor controller. It is arranged in a H-bridge configuration. I'm using 4 MOSFETs. I've used FQP33N10 N-channel MOSFETs and FQP27P06 P-channel MOSFETs. The advantage with these is that they have their own protection diode inside, which is not shown on the diagram for clarity, but normally 4 would be placed like this across each MOSFET. Now the gates here control the direction of the motor. So when the gate is down to 0, nothing happens. If 1 goes high, then the motor will go in one direction. If the other one goes high, the motor will go in the opposite direction. If both go high, then you short the supply out. The 4 resistors used enable the MOSFETs to be switched off by default when there's a floating gate, for example. So the top 2 MOSFETs are P-channel. The bottom ones are N-channel. If you wish to wire this up, I follow a certain method. Now you can see the drains are connected together on one side and on the other. All resistors bridge the gate connection to the source connection. The P-channel sources are connected together and connected to positive. The N-channel sources are connected together and connected to negative. And the gates from the P-channels go to the opposite side.
Here's one circuit that controls the direction of the motor. These are connected to the gates of the N-channel FETs. If I touch the negatives, nothing happens. If I touch 1 to the positive, motor goes around one way. If I touch that onto the positive, motor goes around the other way. If I touch them both on, the transistors would short out the power supply. When I wired this together, what really helps me is getting a CD marker pen and writing P
on the P channel MOSFETs, N for the N channel ones, and SDG for source, drain and gate for every transistor. Field effect transistors are sensitive to static electricity and may be damaged by it. I wore my own anti-static cable when I made the circuit. I decided to use 10 kilo ohm resistors on the gates of the field effect transistors. I happened to choose that particular value. It's not actually that critical. As you can see, I've got all sorts of different ones. 16 kilo ohm would have sufficed, or 27, etc.
There are some problems with this circuit. The Arduino board can only output 5 volts. If the supply was raised to 12 volts to the motor, the Arduino board may not turn on the MOSFETs as expected. Here is an improved design, again omitting the diodes for clarity. The transistors are used to correct the signal to it, so a high input would switch on a direction as you may expect. I have also omitted showing capacitors on the circuit. I suggest an electrolytic capacitor across the battery terminals of maybe 47 microfarads and a non-polarized one across the motor of maybe 100 nanofarads or more in order to reduce the interference from the motor which may affect the operation of the circuit. Across the motor I used 1 microfarad and 1.5 microfarad capacitors, which I just happened to have. You can use pulse width modulation to control the speed or power to the motor. If you are using a 6 volt motor on a 12 volt supply, you may expect to switch on and off the output roughly half the time, although since motors have inductors which oppose changes in current, it will not be exactly half. You would use the analog write command to use pulse width modulation, but this introduces electrical noise to the circuit. I decided not to use either designs as my circuit grew quite large in complexity, and decided to use relays as it simplified my circuit and reduced the electrical noise. Here is my circuit for one motor, which is controlled by 2 relays. I have just shown the switches for clarity. The relays have 2 separate switches with normally open and normally closed connections. One relay switches the direction and the other enables the motor by switching on the supply to the motor. Here is my circuit to control one relay. I would require 4 of these to control 2 motors, which uses 4 outputs from the Arduino board. I have used an N-channel MOSFET here as I can just connect the gate to the output pin, but you could use a transistor with a resistor on the base if you wish. A diode is used to protect the circuit from the relay's back EMF. I have used a 5 volt regulator for the relays instead of powering them from a higher supply voltage while using pulse width modulation. I can just use the digital write function as normal to switch each relay on, which I prefer to do. Another issue with pulse width modulation is that when the supply lowers, I would have to monitor it and adjust the pulse width in order to control the power to either a relay or a motor. Here is the source code to control the tank. I have used code from a previous video in order to receive the infrared signals from the remote control. If you wish to know more, you can watch that previous video. I have my infrared detector on pin 11. I'm using pins 5, 6, 9 and 10 to control 4 relays. You can use other pins if you wish. So I have an enable pin on pin 5, which switches the power to the motor. The direction relay electrically switches the motor one way or the other. I set up all the pins for the relays and switch them all off. This preserves power. I'm using pin 13 for diagnostics, so you can ignore all commands referring to pin 13 if you wish. I need this command here to start using the infrared remote control. As in the previous video, I'm using if and switch statements. Each one of these hexadecimal numbers corresponds to a particular button on my remote control. I have previously decoded the signals in order to get these hexadecimal numbers. This is explained in my previous video. This one, for example, is the OK button, which I'm using to stop the vehicle. I have a move motor function which I have written, taking two parameters, one for the left motor and one for the right. If it is a 1, this would move that motor in a forward direction. A -1 would move it in a reverse direction, and 0 means do not move. I have some motor test buttons which you can either use or you do not need them to operate the vehicle. I've included them for myself to check my own wiring. I need this command just before the if brace closes. That brace encompasses the switch statement. This one is the if statement here. And that is where I have placed this command. If you place it out of the if statement, then your program will not run. I have an all off function here. This switches off all of the relays in order to preserve power. I could have omitted the motor left direction and motor right direction commands and left these relays on, but that would just take up power, although the vehicle would operate in a manner as you would expect. This is the move motor function taking two parameters, motor left and motor right. I start by switching all the relays off. So if motor left is 0, I place the enable pin in a low state, switching it off. If it is 1, I set the direction high and the enable pin high. If motor left is -1, I set the direction pin low and the enable pin high. So this section controls the right motor and is very similar to the motor left commands. And that is how I control the vehicle. Thank you very much for listening.